Hello everyone, welcome to the third video on the first law of thermodynamics. By the end of this video, you should be able to do what Rick tell Morty to tell his parents.
Morty, tell your parents the first law of thermodynamics.
The increment in the internal energy of a system is equal to the increment of heat supplied to the system? Wow, I'm so smart!
But as much as Morty is, it is of little surprise that he has defined the first law of thermodynamics absolutely wrongly. So for this video, we are going to focus in achieving and completing learning outcome D, which basically is recall and use the first law of thermodynamics expressed in terms of the increase in internal energy, the heat supplied to the system, and the work done on the system. So first and foremost, I want to bring your attention to the word increase. So please remember this word increase. Whenever we are defining first law of thermodynamics, we need to use the word increase in internal energy. I'll be focusing on this a little bit, okay, in a while, but let us move on first. But before we jump straight into defining the first law, let us try to relate what we have already learned and how are they related to the first law of thermodynamics. We have learned heat capacity. So we have learned that any heat Q from the heat capacity will actually result in raising temperature of the substance. So when we raise temperature of the substance, what does this mean? It means that the Ke due to random motion is actually increasing. The molecules, the Ke of the molecules due to random motion must be increasing when we provide heat capacity to the substance in raising its temperature. Next, we have learned heat Q from latent heat will actually break bonds, affect intermolecular forces, or allow molecules to be further and further apart. This actually means that the PE due to the intermolecular forces must also be increasing. So the conclusion here that we can derive is we know for sure, dead sure that heat Q will actually affect internal energy. In fact, if we were to provide heat to any substance, what will happen next is that the internal energy of the system must be increasing. Now, instead of heat, what happens if I were to actually compress gas molecules? So I'm going to show you an animation here. So you can see that the piston is actually compressing the region where the gas molecules can vibrate and collide with each other. And you can see from this animation that the molecules is in fact moving faster and faster. So that means that the Ke must be increasing, and hence the internal energy must be increasing as well. This is especially true for ideal gases because we are ignoring potential energy completely for ideal gases, and therefore when we say that we can conclude that the Ke increases, the internal energy must be increasing. And that should make sense because if let's say I'm doing positive work on the gas, which means a compression, the gas molecules must be gaining energy. When I do positive work on the system, I am the one that's losing energy, and my work done will actually contribute to the increase in energy of the system. So in this case, when I compress something, I'm doing positive work on the gas, and the gas molecules should gain energy. The converse should also be true. If the piston is actually expanding, you can see that the work done is actually by the gas in this expansion, and their energy should drop too. The first law of thermodynamics tells us that the internal energy of the system can be changed by the amount of heat added or removed from the system, and also by the amount of work done on or by the system. And this is really just in accordance to the principle of conservation of energy. And now for a proper definition, the first law of thermodynamics states that the increase in internal energy of a system is equal to the sum of the heat supplied to the system and the work done on the system. Okay, you can see here in the proper definition, we uses the word increase in internal energy. However, in terms of equation, we use delta U equals to Q plus W on. Okay, I know that in mathematics, delta actually normally means change in. So when we use the term delta U, it normally means that change in internal energy. But in terms of definition, you will be marked wrong if you actually define the first law of thermodynamics as the change in internal energy being equal to the sum of the heat supplied and the work done on the system. You must define the first law of thermodynamics as an increase in internal energy. So this is the part that I want you to clearly know what you are actually writing when you are writing the equation. Delta U equals to Q plus W on. In terms of a written answer, delta U must refer to as the increase in internal energy. Okay. Also take note that we are using the convention of work done on the gas. There is such a thing called work done by the gas, and if I'm using work done by the gas as the term in first law, the equation must change to become delta U is equal to Q minus work done by the gas. Okay, just like how I showed you in the previous slide, if I'm compressing the piston, the gas molecule's volume decreases, I am doing positive work on the gas. Okay, and if that is the case, we should be using this particular equation. But if let's say there is an expansion, then positive work is being done by the gas. Okay, and later you'll realize that the positive work done by gas is equivalent to saying that there is negative work done on gas. So we really do not need to use this particular equation. I'm trying to highlight here is just to show you that there is a valid equation if I want to define work done by the gas, but the convention for A level as well as for SAJC, the convention of the equation that we are using is the work done on the gas. So memorize this. At the same time, I will strongly highlight that you should always write down this subscript whenever you apply the equation so that you do not accidentally substitute in the wrong value. In questions, sometimes they may give you the positive value of work done by the gas, and you must be aware you should be substituting a negative value into this particular equation then. Okay, so you need to know what we are solving. Do not just solve any random work done and then blindly substitute them into the equation. One of the most important way that we need to learn on how to apply the first law of thermodynamics is via the PV graph. So PV graph refers to the pressure volume graph. So what we are going to do now is to attempt to explain how we can apply the first law equation using the PV graph. So on this slide, on the right hand side, you can see that we have a pressure volume graph. And the way that we are going to do this, okay, is to break down the first law equation and explain term by term. So the first term that we are going to look at is actually delta U. And in definition, delta U actually refers to the increase in internal energy. So if let's say we are saying that the delta U is actually positive, what it means is that the internal energy is increasing. And for an ideal gas, it also means that the temperature is increasing since internal energy for an ideal gas is actually proportional to the temperature because the internal energy is only the Ke of the random motion of the molecules. And then if you can recall the equation for ideal gas, internal energy is actually equals to 3 over 2 nkt or 3 over 2 nRT. And if we were to use the ideal gas equation, PV equals to nRT nkt, we can also similarly derive the equation to become 3 over 2 PV. So if let's say we are looking at a fixed mass of gas, meaning my N or the number of molecules, big N, or the number of moles of gas, small n, is constant, and we are looking at the change in state from A to B. Okay, so in this process from A to B, we can see that the pressure is actually constant, yet the volume is actually increasing, and therefore we can actually conclude that the internal energy is increasing. How? By looking at the equation 3 over 2 PV. Okay, so since pressure remains constant, volume is increasing, we can conclude that the internal energy is increasing. Alternatively, we can also look at the ideal gas equation PV equals to nRT. And since we are talking about fixed mass of gas, my N is actually a constant, but my pressure is also a constant based on the change in state from A to B, while volume is increasing. So based on the left-hand side, we know that the left-hand side must be increasing. So on the right-hand side, N being a constant, R also a constant, I know that my temperature must also be increasing. And the fact that we also know that ideal gas U is proportional to T, we know that temperature increases means that internal energy must also be increasing. So it also means that the delta U must be positive. So the converse is also true. When we look at delta U being negative, it also means that U is decreasing and temperature for ideal gas must also be decreasing as well. So once again, the equation U equals to 3 over 2 PV. So if this time round, we are going to look at the ideal gas changing from state B to state C. So in this process, we can see that the volume is actually constant, but the pressure is decreasing. So using the same equation, we can conclude that the internal energy is actually decreasing. So once again, if we were to look at ideal gas equation or whatsoever, since we know that the temperature must be decreasing, we also can conclude U is decreasing and therefore delta U must be negative. So now, I have talked about two examples already. Why don't you try rationalizing? What about from C to A? When the ideal gas is changing state from C to A, can you conclude whether the internal energy is increasing or decreasing? Okay, what I'm going to do is to tell you the answer that U is actually decreasing from C to A, but you need to derive the argument yourself. Okay, if you cannot, then feel free to look for a tutor to ask them to explain in this case. So we have already talked about the scenario where delta U is actually positive and negative. So naturally, we're going to talk about the third scenario when delta U is actually zero. And if delta U is actually zero, what it means is that there is no change in internal energy. And for an ideal gas, when delta U is zero, it also means that the delta T is zero. That means there is no change in temperature. And there is a special term to describe such a process, and it is called the isothermal process. You actually need to know this term very well. Okay, so for example, whenever the question mentioned the word isothermal process for a fixed mass of gas, what you must be able to conclude is that throughout the process, temperature is actually constant, delta U is always zero throughout the whole process. And if you actually recall from chapter 11, I forgot whether is it Boyle's law, Charles' law, or is it the Gay-Lussac law, but using the ideal gas equation PV is equals to nRT, and we know that an isothermal process means that everything on the right hand side is actually a constant, of course also assuming for a fixed mass of gas. So if let's say it's an isothermal process, we can conclude that P is actually inversely proportional to the volume. And if P is inversely proportional to the volume and we need to plot a PV graph, or in this case somehow we use a VP graph, you must be able to see that you will actually get this kind of curve. Okay, and the way that you need to understand this curve is that for every point along the curve, every point it has the same temperature, every point the gas, every point is having exactly the same internal energy as well. Okay, so this is what it means by the isothermal process. Throughout the whole process, the internal energy is unchanged, the temperature is unchanged. And how can you see this? Let's take for example, okay, we know that temperature constant means PV must be constant for a fixed mass of gas. So therefore, you can randomly take one point. I take this point for example, I see that volume is 12, pressure is 1. So if I multiply the two of them, I get 12. So I take another point, say this point. Okay, volume is 6, pressure is 2. 6 times 2, it is also 12. It must be constant. If I choose a third point here, 4 and 3, I multiply together, it is also 12. So in general, in A level, for any curve, once you can prove 3 point is actually constant, you can prove that in this case, temperature is actually constant. Okay, so carrying this idea, if let's say I have a higher temperature, then I must be getting a curve as well, just that this curve will be above the original line. Okay, and if let's say we are talking about a constant temperature, a process where the constant temperature is actually lower, then we should also get a similar curve, but actually below this line. Now, that being said, it doesn't mean that you see any curve on the PV graph and then you can conclude that it is actually an isothermal process. It's like if you actually see some handsome man on the street, you cannot immediately conclude his name is Mr. Lin as well. I mean, the person can also be Mr. Roland Lee. Okay, so for example, if let's say I'm going to draw some random curve, so this random curve, okay, this is also a curve, but this process is definitely not isothermal. And how do you prove it? You can just randomly choose 2 points, and you can see that the pressure multiplied by volume will not be constant. And therefore, even though this is a curve, it is definitely not an isothermal process. And one last thing before I move on to the next term, heat, which is represented by the notation Q. Okay, I want to talk about this thing called the cyclic process. By cyclic process, what we mean is that the fixed mass of ideal gas perhaps starts from point A, state A, and then it goes through a process to B and then to C, and then finally back to A. Okay, so basically the ideal gas has changed state from A, B, C back to A. After one whole big round, it comes back to exactly the same state. And if you can actually recall in the previous video, we have already mentioned that internal energy actually depends on the state. And since having gone one big round and coming back to exactly the same state means that the change in internal energy for the whole process from A to B to C and then back to A, delta U must be 0. Okay, basically when I come back to the same state, I have the same pressure, I have the same volume, and if I use equation U equals to 3 over 2 PV, despite the fact that A has moved to B to C and then back to A, after one whole big round, I come back to exactly the same state. So therefore, U must be constant, delta U must be 0. This is actually an extremely important point. Okay, circle, highlight, bold it, do whatever it takes for you to remember this point. Etch it into your mind permanently right now. or at least until A level ends next year. Okay, and the reason why I ask you to do so is really because for almost every question that is relating to first law and PV graph, okay, if the question is about first law and PV graph, it is very likely that you need to recall these facts in order to solve the question completely. And I'm talking about like easily one part, 3 to 4 marks. Okay, and if you forget this pointer, you would never be able to score 100% of the question. Okay, I'll be coming back on this and stress on this point later when we are actually doing examples, especially example 12. Now that we are done with delta U, we'll move on to the next term Q, which actually represents heat supplied to the system or heat transferred into the system. So when we have Q that is positive, it means heat is transferred into the system. And by system, we normally means ideal gas for A level. And then if let's say we have Q that is negative, it means that there is heat removed from the system. And before I move on to the last one, what does it mean by Q being zero? There's one thing that I want to highlight right now. Okay, what we are talking about right now, heat supplied to the system is represented by Q, not delta Q. Why do I want to say this is because I have seen way too many students who are very careless in writing their equations out. They will write the first law of thermodynamics as something like delta U is equals to delta Q plus delta W. There is no such thing, okay? Delta Q represents change in heat. It is not heat supplied. And in first law, we want Q to be simply the total heat supplied, not the change in heat supplied. So please be careful of how you write the equation. It is actually penalizable. The correct way to write the first law of thermodynamics is delta U equals to total heat supplied Q plus the work done on the system, not the change in heat supply or the change in work done on the gas. Okay. So now with that covered, we move on to the last one, Q equals to 0. And for Q equals to 0, that means there is no net heat transfer. And the technical term to describe this process, Q being 0, is called an adiabatic process. Now, I don't actually think that A level actually use this technical term somehow, but I don't know why. But your tutor may on and off use it, so it is actually good for you to know. But how A level, if A level doesn't describe the process as adiabatic, how they will describe this process, for example, will be the system is well insulated, or they will say something like the process is completed in a very short period of time. You may be thinking, how come short period of time means Q is equal to 0? Well, the reason is really because heating is something that takes time. I mean, for example, it also takes time for you to steam a fish, pan fry your prata, or boil your mee siam. Okay, it is not like once you put the thing onto the stove, there's provided, you switch on the stove and heat is provided, and immediately the food becomes cooked and piping hot. That is not the case, okay? For heat transfer to take place, it actually takes time. And hence, if the process is taken place in a very short amount of time, then there is no chance for heat to transfer, and that is why Q is equal to 0. Now, the consequences of knowing the process is adiabatic, or the process is taken place in a very short amount of time, or the system is well insulated, is that once we know this information, in order to apply first law, the equation is simplified. The equation simply becomes delta U equals to W on the gas only, work done on the gas only. So knowing all this information allows you to solve the equation with a simplified first law of thermodynamics. Otherwise, if you actually did not know that, you may still try to solve using delta U equals to W plus Q. And then you do not know what Q is, and then you get stuck there. Okay, so it is pretty important to know keywords, well insulated, taken place in a very short period of time, or if suddenly A level uses the term adiabatic, you must know it represents Q is actually 0. So now move on. This slide is something extra, but it's trying to bring an important message. So the question here is, when a piston containing ideal gas is insulated, does it mean that the temperature of the gas will always remain constant? Okay, and the answer to this question is that it is a definite no. Insulated actually means what? Insulated means that there is no heat exchange with the surrounding. Therefore, Q is 0. It's an adiabatic process. And all it means insulated is really just means Q is 0, nothing else. Well insulated definitely doesn't mean work done on the gas is actually 0. And if we think about it, okay, in A level, when we apply the first law of thermodynamics, work done on the gas, if it is actually positive, delta U is equal to 0 plus W on, which must be a positive number. Okay, and if we are talking about ideal gas system, when the delta U is positive, it means that it has gained internal energy. And when it has gained internal energy, it simply represents that the temperature must have increased. So despite the fact that it is actually a well-insulated system, if I actually do work on the gas, delta U will be positive. If it's an ideal gas, we are sure a gain in internal energy means that temperature has increased. And the converse is also true. Okay, if the work done is actually negative, that means the gas is expanding. Delta U is equals to 0 plus work done on the gas, and work done on the gas being negative give me a negative delta U. And that would means temperature has decreased for an ideal gas system. What you have learned in O level perhaps really means insulated means temperature is constant. Okay, and that is really because in O level you learn simpler stuff. Okay, you have a simplistic scenario. For example, maybe we are just talking about solid and liquid. And for solid and liquid, it cannot be compressed nor expand significantly in volume. And that is why work done component is totally ignored. You will learn this, I'll describe this in detail in a while. But understand that if something doesn't change in volume, work done should be zero. Okay, but for gas, which can significantly be compressed or expand, we cannot ignore the term work done. So if you are the kind that is remembering that insulated simply means temperature remain constant, please throw away that context here. Okay, it will not be correct. Insulated simply means Q is equal to 0. It does not mean delta U is equal to 0. Okay, and if delta U is not 0 for an ideal gas system, temperature can change. So for A level, heat supply is not the only determinant of delta U, delta T for ideal gas. Work done on the gas can affect U and hence T as well. Okay, so insulated simply means Q0, doesn't mean delta U0. So talking about all this brings us to the next term, the work done on the gas, and also the next point. How come work done on the gas can actually increase in temperature? So let us illustrate this with a video. In this video, the person will be setting up the piston. This setup is actually known as the fire syringe. So you can see here that the person is actually putting a tinier inner cylinder inside this outer cylinder here. And we actually call this a double layered piston. So what happens here is there is a layer of gas between the inner smaller cylinder and the outer cylinder. So this layer of gas is actually providing some form of insulation, and later the person will actually put in some tiny pieces of cotton wool inside this inner cylinder. So some cotton wool inside this inner cylinder. Then what will happen next is you'll push in a piston very quickly inside this smaller inner cylinder, basically compressing the air inside the inner cylinder quickly. Quickly, in other words, means in a very short amount of time. And I hope you can remember what this phrase is trying to tell you. And also, when I say I compress the gas, meaning the volume of the gas is decreasing, the work done on the gas is positive. I am losing energy, the gas is gaining energy. When I say that work done on the gas is positive, remember this. So anytime when there is work done on the gas that is positive, it means that the gas is being compressed, the volume of the gas is decreasing, and the gas is gaining energy. Okay, anyway, later focus on what happens to the cotton wool. So you did saw the cotton wool fire up, right? Can you think of why this actually happens? I'll let the expert explain in the next video.
So, Nigel, what have we got here? Oh, we've got something called a fire syringe.
And what does it do?
Oh, well, I'll show you what it does. Some cotton wool in there.
Okay.
I'm just going to compress the air in it, and hopefully it will. I don't know what it's going to do.
Wow.
That's pretty cool.
You made a spark in there. Was there any source of fire, like a match or anything down there?
Well, as you can see, it's pretty transparent. There was no match in there. It was actually just the compression of the air on top of it, which was able to ignite the cotton wool that we had in there.
So you're saying if we compress air,
we can make it hot enough to ignite cotton?
Yeah, because air is made up of particles, so when you're actually compressing it, you're forcing those particles to collide closer together, which is actually going to raise the temperature in the inside of that tube there.
Okay, can you describe the apparatus for me?
Well, all there is there's a glass chamber in there where the cotton wool sits, and as you can see, there's this piston that moves up and down into that glass chamber, and as it moves up and down, you can actually compress the air.
So it's like a little plunger.
Like a little plunger, yeah.
Okay, so why don't we set one up so we can do it again?
Do it again? Okay, I'll clean the remnants out.
What are the tricks here?
The trick is to get not too much, but not too little cotton wool, and it's good to get it aerated so that there's a lot of air around it, so it makes it much easier to ignite, just like a good fire.
Is it just me, or do you feel like we're on a cooking show?
I feel like we're on a cooking show, yes.
Who do you think would be Jamie Oliver in this situation? Would it be you or me?
I'm more manly, so...
He's more like Nigella Lawson, let's face it.
That's a good play on words. I wish.
All right, we're ready for this?
Yes. Simple as that. Obviously no matches, no switches, no anything.
Okay.
We'll try it. Again?
You want me to try?
You can try it.
Yeah,
do you have the strength?
We're going to find out,
We'll
aren't we?
find out. This is going to be awkward for Derek, I think.
Okay, so what I'm going to try to do is compress the air in there, and by compressing it, I'm going to increase its temperature because we're pushing all these air molecules together. And if I get it hot enough to the ignition point of cotton, hopefully the cotton will catch on fire.
Yeah, I've heard that the auto-ignition temperature of cotton is about 400 degrees Celsius, so you can get quite enormous amounts of temperature from a very quick compression.
3, 2, 1.
Oh, surprise.
Beginner's luck. Yeah, check that out. So I guess we could generalize and say if you do the compression quite slowly, then, well, there's time for the heat to escape out of the air. And so we don't actually get a high enough temperature to cause the cotton to ignite.
Yeah, and there's actually a word for that. It's called an adiabatic compression. That's the one where there's enough heat generated quickly enough so that we can get that auto-ignition.
Yeah, so an adiabatic compression would be one in which the heat doesn't escape from the gas.
Doesn't have the time to.
Absolutely.
Yeah.
All right. Well, let's go see if we can auto-ignite some other things.
Yeah, maybe some hair.
Okay.
Maybe not a good fuel source.
Alright, so basically what happens is positive work is done on the air because there is a compression taking place. So therefore, the air actually gains energy, causing its internal energy to rise. So if you actually make sure that we compress it quick enough, there is simply no time for the heat to escape to the surrounding. So basically Q is equal to 0. It means it's an adiabatic process. So using the first law of thermodynamics, we have delta U equals to Q plus W on the gas. And because Q is 0, and because we are doing positive work done on the gas since it's compression, we get delta U equals to positive. That means that there is a gain in internal energy. And this gain in internal energy implies that a gain in temperature has taken place, and therefore the cotton wool actually ignites. And the converse is also true. So in this video, the bottle actually contains alcohol. And then you see this guy on the left pumping more air in, essentially compressing the air inside the bottle, basically doing positive work on the air inside, which heats up and helps to evaporize a lot of alcohol vapor. And then you see that when the stopper opens up, you see clouds inside forming. What has happened? And then it puts the stopper back and the guy compressed air inside again, the cloud disappeared. What has happened? Okay, so basically, the first time when the guy on the left compressed the air inside, he helps to evaporize a lot of alcohol into invisible vapor. And then when the stopper is opened up, the pressurized air expands suddenly. So this time round, what happens is the gas that is doing the work against the external environment and pressure, and hence the gas loses internal energy. So basically, when the gas expands, now the work done on the gas is actually negative, meaning the work done by the gas is actually positive, and hence internal energy drops, temperature drops, and the alcohol invisible vapor condenses into tiny droplets, which becomes the visible cloud. And then after the guy in the middle put back the stopper, the guy on the left compressed the air inside the bottle the second time. Work done on the gas is now positive, and therefore the cloud heats up and turns back into the invisible vapor again. We've basically explained everything through the videos on the work done on the gas already, but anyway, let us quickly summarize. So W on actually represents work done on the system, And when we have W on that is actually positive, it means work done on the gas is positive. And for a fixed mass of gas, there must be a compression, meaning there must be a drop in volume. And when there is work done that is actually negative, meaning the work done on the gas is negative, for a fixed mass of gas, there must be an expansion, meaning to say that there is an increase in volume. And when work done on the gas is positive, it also means that the work done by the gas is negative, or vice versa. So therefore, the word positive is actually important, so please add them into your notes. Finally, when work done is actually zero, it means that the volume must be constant for the fixed mass of gas, no change in volume. And we call this process isochloric or isovolumetric. Otherwise, if the gas does expand and yet does no work, meaning to say that the work done by the gas is actually zero, it must be expanding into a vacuum. And the consequence of all this is that the first law simplifies and the equation becomes simply delta U equals to Q only, very similar to adiabatic process. So with that, we have really covered all the three terms in the first law of thermodynamics. But this being a very content-intensive lecture video, so let us quickly summarize the things that we have learned so far. So essentially, we have learned three key processes. Isothermal. So for isothermal, it means that the temperature is constant, delta T is zero, and that also implies that the delta U is zero for ideal gas. And therefore, when we apply the first law of thermodynamics, we get zero equals to Q plus W on. And when we rearrange the formula, we either get W on equals to negative Q or Q equals to negative W on. So there is actually a meaning behind it. So the way you should think about this rearranged formula is that, for example, any positive work done on the gas did not contribute into gaining internal energy, but instead has been lost as heat to the surrounding. Or in another way, you can think of it as any heat supplied are lost through negative work done on the gas. Or perhaps it's actually easier to think of it as any heat supplied has been lost as positive work done by the gas. So therefore, the internal energy can actually remain constant. And then we also have learned adiabatic, or in other words, well-insulated or short period of time, meaning to say that the heat supply is actually zero. And important to note that it is not delta Q equals to zero, but just simply Q equals to zero. So therefore, the first law of thermodynamics becomes delta U equals to W on the gas only. And then finally, we talk about isovolumetric, or in other words, isochloric, basically means constant volume. So therefore, delta V is zero. And when there's no change in volume for a fixed mass of gas, then the work done on the gas or by the gas equivalently must be zero. So therefore, the first law becomes delta U equals to Q only. Some other important idea, compression is equals to work done on the gas being positive. It means the gas gains energy. Expansion means the work done on the gas is negative, or in other words, there is positive work done by the gas. But it all means that the gas actually loses energy. So with all this learned, let us attempt to do at least one example in this video, example 5. So example 5, please pause the video and try to think about it on your own. Don't spend too much time on it because it's pretty easy. I'll be assuming that you have already done so, and I'm going to continue talking about this example now. So for the first scenario, the system of ideal gas gives out 200 joules of heat without a change in volume. Okay, so when I give out 200 joules of heat, that means there is heat loss to the surrounding. So therefore, my Q must be negative 200. And since there is no change in volume, that means the work done on the gas or by the gas must be zero. So therefore, delta U is simply the sum of Q and W on, we get negative 200. And then in the next scenario, we have a system of ideal gas does 100 joules of work on the surrounding at constant temperature. So it does 100 joules of work on the surrounding, means that you can infer that the work done on the gas should be negative because it is doing positive work on the surrounding. That means the work done by the gas should be positive, the work done on the gas should be negative. And since it is constant temperature, my delta U must be zero. So therefore, Q can be derived by taking delta U minus work done on the gas. So 0 minus negative 100, it gives me positive 100. The third scenario, 50 joules of work is done on the system of ideal gas while 50 joules of heat is removed from it. So I know that 50 joules of heat is removed. So therefore, my Q is actually negative 50. But 50 joules of work is actually done on the system of ideal gas. So therefore, W on is actually positive. And therefore, we get delta U equals to 0. And this is an example of a isothermal process as well. Okay. So finally, the last example, 70 joules of heat is supplied to a system of ideal gas without a change in temperature. So once again, there's no change in temperature. It implies that it is an isothermal process. Delta U must be 0. And since there's 70 joules of heat supplied, therefore Q should be positive 70. And therefore my W on is simply rearranging delta U minus Q. And therefore I get 0 minus positive 70. Therefore my work done on the gas should be negative 70. Okay, so we are done discussing about the first law of thermodynamics, but we have not done too much in applying them via the PV graph. So in the next lecture video, we are going to focus exactly on that, on how PV graph and how it is actually related to the first law of thermodynamics.
Did you get any of that?
Sure, Bo.
Understand?
Your online source of
Interesting physics lecture.